We shipped it to production, and someone came to me and said, this is wonderful, but you haven't accounted for the context length at all. When I'm trying to set a threshold for this kernel, I have to change it all the time because it's not normalized. So then I had to go away and go, okay, well fine, let's normalize by the sequence length of KV, which is where the divide in that slide comes from, was basically because somebody sent me an angry message on Slack and said this is really hard to use.
AI Native DevCon is back.
The leading event for engineers and organizations moving agentic development into production.
Join us on June 1st and 2nd at the Barbican in central London.
For 2 full days of workshops, fascinating talks, and great company.
You'll hear from some amazing speakers, such as Ryan Lopopolo from OpenAI, Dana Lawson, CTO at Netlify, Justin Cormack, the ex-CTO of Docker, and Birgitta Beckler from ThoughtWorks.
They'll join speakers from Anthropic, NVIDIA, GitHub, Cisco, Meta, Adobe, Mozilla, and many more.
This is a practitioner-led community event and would love to have you join us.
Head over to ainativedevcon.io to grab your ticket.
We'll see you there.
This talk might give us a little bit of whiplash, actually, because I feel like we're going to go from very high-level kind of AI stuff to right into the depths of attention kernels and optimization and stuff. So should be fun. I will also give some credit to Claude. Probably, like everybody here, is going to have to do at some point. I did take a different approach, though. So what I tend to do is write the slides myself, and then I have Claude tell me just how terrible they are, and then go through and fix them all. So a quick agenda on this talk, really. So this is all about what I refer to as long context inference. And it's effectively an optimization exercise for the attention kernel in CUDA, some benchmark results, and kind of takeaways, really. So I talk about long context. So what do I mean by long context, and why is it important? So not so long ago, really, kind of like an 8,000 token context window was like considered a really big deal. And today, now, like frontier models like Claude Opus, they ship with context windows up to a million tokens. So that shift isn't really just a number either. It kind of changes what you can do with the model. I know certainly for me as a developer, the way I work now is totally different to the way I worked probably 18 months ago, 2 years ago. Just very rapid pace of change. So some of the kind of things we can do now are listed on this slide. So like more complicated system prompts, document analysis. One of my favorite uses probably is summarizing those horrendously long email chains that I come into in the morning that I definitely do not have time to read. Really large code bases. Probably the big one for me is as a dev tech, I work on all 3 of the inference libraries, so SGLang, VLLM, TRT-LLM. I've probably touched all of those in the last 3 or 4 months, and every time I come back to one of them, it looks completely different. So usually the first thing I do is ask Claude to tell me what's changed and how do I find what I'm looking for. And kind of attention cost, like the cost of the attention kernel, scales linearly with like sequence length per token, which means it's quadratic, really. And kind of every new token generated has to attend to the previous context, and at 1 million context, basically that gets really expensive. And this is what this talk is about, kind of addressing in a way. So anybody who's super familiar with the math behind attention is probably going to be really bored by this slide, but I didn't want to assume that everybody would know exactly how it works, because if you don't kind of have an idea of this diagram, you don't really understand the optimization. So kind of the intuition is obviously that every token that the model is processing, attention is basically asking which of the other tokens in this sequence are relevant to me and what does that tell me. So Q is your queries, which is the question that each token is asking. K is kind of a label associated with each token, and V, the value, is what that token contributes if it's selected. So if you multiply Q by the transpose of K, you get what we call like a matrix of attention scores. And this is a sequence length by sequence length matrix of compatibilities. And then you do an operation called softmax, which we're going to come to in more detail in a second. The key in the title of this talk, softmax, is kind of important here. And that gives you basically a probability distribution. Q times the transpose of K is a matrix multiplication, which we really like on GPUs. We have tensor cores that make those really fast. And then softmax has this exponential. Now it's interesting because actually on some of our hardware, we're actually bottlenecked by the exponential more than we are by the matrix multiply. Kind of on the right here, we have what we call multi-headed attention, which is this attention process applied to multiple heads in parallel. Yeah. So now a little bit about softmax. I've just said that softmax is really important. The algorithm here, like online softmax, came up with by a guy I've cited on this slide, Maxim Malarkov. He's in my team, he's super smart, and I think he probably gets some personal satisfaction every time I mention his paper at one of these talks. So the problem with naive softmax is basically that you need a global max across all of the keys. And that means, in order to keep your numerical stability so that you don't overflow. The problem is that you don't know the max until you've already processed all the elements, which means you need at least 2 passes. And over this big matrix, that thing gets really expensive. So thanks to Maxim, we have this online softmax, which allows you to process this in a single pass. And the idea is basically you have to keep a running max and do some checking. That means you can do a correction at the end. Now, this running max really is super important because we use it to check whether we can skip the softmax later. So we should really pay attention to that. So there's kind of 3 properties to keep in mind. Single pass, which means we don't have to materialize the full attention matrix in memory at any one time. This is kind of one of the key optimizations behind flash attention. It's like reading that matrix over and over again is really expensive. Numerically stable is super important as well. So naive softmax requires 2 passes, 3 operations per tensor element. Safe softmax subtracts the max to eliminate the overflow, but that also requires 3 passes and 4 memory operations per element. Online reduces this back to 3. So we talked about attention being expensive. The really interesting part about attention is that despite being super expensive, it's actually also very sparse. So this kind of diagram on the slide here is showing you basically the result of Q times K. And these kind of squares that are highlighted in gray are the ones that are like, I don't know really what to say, it's kind of like an informal term, but important. So it's kind of weird is that we do all of this work, and yet a lot of it doesn't really contribute to the result. So oftentimes attention, like I think I've cited on the slide here, in some cases it can be up to 96% of your workload. So the idea that I'm saying that a lot of this work is actually wasted is kind of really not ideal, right? So this is changing of tack a little bit. So the kernel I'm trying to say, this presentation is basically an exercise in kernel optimization. And the kernel that I worked on is a kernel from NVIDIA that we called FMHA, which is fused multi-headed attention. It's a bit like flash attention, except I think we support a bit more. I think a lot of the key optimizations are the same. And it turns out that actually, in order to write a good attention kernel, you can't really do that in one kernel. You need like hundreds of attention kernels that are optimized for different scenarios. So for example, your context kernel versus your generation phase kernel require very different optimizations because when you're doing generation, you only generate one token and then you're attending to the entire previous KV cache, and that changes the shape of your matrix multiply. So basically what we decided to do was we wrote a code generator called TRT-LLM-gen, and basically we used that to help us maintain all of these kernels because we realized it would be easier to write one generator and then generate the kernel we need versus have me maintain potentially thousands of attention kernels. I think currently, off the top of my head, inside TensorRT-LLM on GitHub, I think we have 4,000 kernel binaries for attention. And that often blows up even more when somebody like me comes along and says, hey, can we get a skip softmax variant of all of these, please? And then you multiply it by 2. The kernel is warp specialized. For anybody who doesn't know what that means, a warp is basically a group of 32 threads that operate in parallel on the GPU. And when we say warp specialized, we mean each warp gets a different job to do, And this is kind of a method to allow us to keep all the different execution units on the GPU busy. So memory, MMA, your softmax unit, not softmax unit, multifunction unit, which you use to calculate softmax. So for example, in flash attention, often what happens is we use one warp to load tiles of the matrices, another warp will be doing matrix multiplies, somebody else will be doing softmax, and then somebody else is writing out the output. And kind of synchronizing all of these very different stages of the pipeline is super hard to do by hand, which also kind of lends itself to a code generation kind of method, just because it's so much to hold in your head as a programmer that I don't necessarily think it's feasible to do by yourself. So there are more tasks in the FMHA kernel that are listed on this slide, but basically when I say a task, I mean this is something we're getting a specialized warp to do. And the key ones that we care about are kind of listed in this table. So like the load task does, well, it's kind of in the name really, it loads data from global memory. And this is basically for reading Q, K, and V. We have the MMA task, which issues instructions to the tensor cores, softmax task, and that reads the result of what we call BMM1, which means batched matrix multiply. And BMM1 refers to Q times K. So if I say BMM1, that's what I mean. If I say BMM2, it's the P times V matrix multiply. And we finally have the correction task, which is relevant to Maxim's online softmax. So to kind of get an idea of why this works or what this optimization is going to be, and I promise this is the only maths we're going to do together in this presentation. I said before that a lot of the attention values that we are calculating end up being 0 after softmax or close to 0. So that means then when you do your P times V BMM2 that something interesting happens. Say you have a row of this matrix that is all zeros. What does that mean for your result? Well, it turns out that that also means that the result of that matrix multiply for that row is also 0. So what if I told you we could just, not bother doing it, because what's the point? It's not changing the answer anyway. So I think anybody who's familiar with flash attention would have seen a diagram like this before. Basically, to avoid realizing the full attention matrix in memory, we break it up into tiles. That's kind of shown in this diagram here, where you do 1 Q times K for a given tile. Then you softmax that tile, multiply it by V, and accumulate it into the output. So that's kind of the loop. It makes it very memory efficient. What it doesn't do, however, is work out whether that attention calculation is actually worth doing, which is kind of what I keep coming back to. So many of these tiles are producing softmax values that are essentially 0 or close to 0. Something that we'll come back to later is the idea that you can tune how aggressive this skip is, but that obviously has trade-offs in terms of accuracy and performance. So this isn't a corner case either, like I said before. Attention is sparse. If we go back to that vertical slash diagram from before, most of those squares were white, not gray. So essentially, we have a really complicated kernel that processes loads of tiles, but a workload where most of those tiles don't actually matter. And we call this kind of skip softmax. It turns out actually that we're skipping a lot more than softmax, and oftentimes softmax is not actually the most expensive operation that we're skipping, but well, we've named it now. So the key insight here is how can we skip the tiles cheaply using information that we've already calculated. We have this running max that we're keeping for softmax, for online softmax, and that is a result of Q times K, which we've already done. So kind of calculating this value is not additional work. So when a new tile arrives, we do this batch matrix multiply, and you take a row-wise maximum of each tile, that's a local max, and you compare that to the running max. Now this is cheap because we were doing this reduction anyway. But anyway, like we see in this kind of equation here, the key is if your local max is much less than your running max, and by much less I mean the difference would be a large negative number, then the result of the exponential is basically 0. Now that means if all of the softmax values of that tile would be near 0, that entire tile contributes nothing to the output. So we can just set them to 0 and not do a bunch of extra work. So if you kind of look at this diagram here, you ask yourself this question: have we triggered this threshold or not? If we haven't triggered it, then we're very sad and we have to do all this work. And if we do trigger it, we can skip the exponential, the normalization, loading of the v-tile, a matrix multiply, and the correction step. And the kind of really nice thing about this is that you don't need to do any additional training on your models. It's just an inference time thing. You can just deploy it and use it. So you save in various ways, really, and that's kind of what this slide is trying to say. You may hear like a kernel developer talk about a kernel being compute bound versus memory bound. When we say that, if you're compute bound, it means you spend most of your time doing math, and that's kind of your bottleneck. Whereas if you're memory bound, you're kind of bottlenecked by, well, the memory subsystem. Now, if we kind of walk through this, basically what I've got is a diagram here that shows you all the different parts I've just said we're skipping, and what exactly you save from skipping them. So when you skip the softmax and the normalization, that's a compute saving. You also have to keep statistics to do your correction. That's also a compute saving. The really interesting one is the v-tile, because that's the only memory saving here. And in fact, for some versions of this kernel, we don't actually skip this, because if it's a compute-bound kernel, you're not bottlenecked by that load. So delaying the warp, that then has to decide whether to skip or not, actually hurts you more, because it doesn't buy you anything in a non-memory bound situation. P times V saves you tensor cores, which obviously we care about. And then the correction we've kind of already talked about. Interestingly, skipping the correction is an optimization that already existed, or we did it prior, and I think flash attention does it as well, but it turns out if you're skipping softmax, you can also combine it with this other optimization. So kind of the skip condition, like how does it work? I said before, a warp is basically a group of 32 threads. So each thread needs to decide whether to individually skip, because the way we kind of write this kernel, or the version of the kernel that I care about, each thread basically has a row of the tile when you're doing this softmax calculation. And you do this exponential. That is effectively measuring how much smaller is this tile's maximum versus the running global max. And this threshold is user tunable. It turns out actually that picking a good value for the threshold is really hard. When I was just developing the kernel, I didn't really fully appreciate that, right? I would just set a value for my unit test, check it against a reference, and then go, oh, great. Then we shipped it to production, and someone came to me and said, this is wonderful, but you haven't accounted for the context length at all. So it turns out that when I'm trying to set a threshold for this kernel, I have to change it all the time because it's not normalized. So then I had to go away and go, okay, well, fine. Let's normalize by the sequence length of KV, which is where the divide in that slide comes from, was basically because somebody sent me an angry message on Slack and said, this is really hard to use. So after that, basically what you need is all of the threads or all of the warps that are processing a tile need to agree. So to do that within a warp, we have this handy intrinsic called allsync, which is really fast. But it turns out to do softmax effectively, you need 4 warps, and multiple warps can't talk to each other. So you have to do some atomics in shared memory, which is a bit slower, but that's just the way it is. So I've probably spent now close to 15 minutes telling you all about this kernel and how it works. And really the question that everybody probably has is, well, this is all well and good, but does it actually work in practice? So the does it work part of the presentation is basically the next few slides. And I'm going to frame it essentially as specific questions that we need to answer. These questions being, well, what's the overhead when we don't skip? How fast is it for context or prefill kernels? And how fast is it for generation or what we call decode kernels? And even if your attention kernel is faster, does this actually show up end to end when you're on a model? Because if your bottleneck is something else, you can make attention as fast as you want. It doesn't really help you in any way. So this kind of graph shows overhead analysis. And basically what we're kind of seeing, or what I saw when I profiled this, is certainly a lot of the time that the overhead is basically a function of profiling noise and is actually really hard to capture. This is not so much the case for generation kernels, where it's a bit slower. And what this graph is showing is basically 1 is no overhead, and then lower than that is slower. But for the generation case, we're still actively optimizing this. It turns out the memory bound case is really hard because the matrices are really small. So there are 2 kernels, or 2 types of kernels we really care about. Context is when you do your prefill. So this is before you've got your KV cache and when you generate your KV cache. For this, I focused mostly on BF16 and FP8. And what this is on the x-axis, we have what we call sparsity. And sparsity is effectively what percentage of the attention tiles have we skipped. So 100% is we did no work, and 0% is we didn't skip at all. You can never skip the first tile, otherwise the threshold check doesn't work. And I suspect that if you skip all of the tiles, everything probably collapses into garbage anyway. So I think the extremes at either end of this graph are not particularly useful. What we care about probably is this area in the middle. FP8 speedups are lower than what we got for BF16, and that's kind of a consistent theme throughout this talk, and we're still kind of investigating that. Generation is a very different kernel to prefill, it turns out. Basically, because you're attending to the entire KV cache, but you're only receiving or processing one new token, your Q matrix is really skinny, and the work then becomes dominated by loading K and V instead of your matrix multiply. This kind of brings us back to the cascade savings diagram I had before. Stage 3 is basically when you skip a tile, the V tile is not loaded. Kind of in the context kernels, most of the time, I think I mentioned before, we just don't bother doing this because the extra weighting is not worth it. But on generation kernels like this, if you don't do the load skip, you get no benefit at all. I think partly as well why FP8 benefits at least less in this case is I think we're just moving less data, but that's a bit more clear to me than the prefill case. Finally, end-to-end testing. I didn't run these tests, but I think an esteemed colleague of mine tested, I think it was Quen 3, on two benchmarks called long bench V1 and long bench V2. I think it would have been negligent of us to not use a long context kernel to test this. So for long bench V1 versus V2, for V2 we could only fit a batch size of 1 just because the context is so long you end up ooming the GPU if you try to run multiple prompts. The speed up shown in this graph is based on time to first token. We're still working on the time per output case. And I think what's really interesting is that you can actually get a large amount of the speed up shown in this graph without taking too much of a hit to your accuracy. The problem is that because this is model dependent, it means whoever's deploying that has to spend a load of time calibrating it to try and work out what their acceptable threshold is. Though maybe now you just get Claude to do it. And so where can you use this? So right now it's in TensorRT LLM and in a library I think that NVIDIA maintains called FlashInfer. It used to be, I think it was the result of a PhD project, but somehow we ended up taking it over. But FlashInfer has basically become the library that we open source all of our kernels through. And through FlashInfer, this is available in SGLang as well. It's going to be available in VLLM. I happen to work with the guy who's adding it. I think he's like halfway through. There are some PR numbers on this slide if anybody's interested. There is some code snippets here, and what's kind of nice about this, we don't really need to walk through them in detail. What's kind of nice, basically, is that to use this, the only thing you need to specify is this threshold. Your API doesn't really change. There's no like hairy kind of change to all of your scripts or anything. You can just set a value and kind of go. You just need to spend some time deciding whether you're happy with the results or not. So what are the key takeaways? So doing this like skip softmax eliminates loads of redundant compute and memory traffic. The threshold was designed to basically be a really clean knob that you can tune. It's kind of easy. I think I have scripts at home that are just loops over this threshold measuring different performance things. That's how we kind of got most of the graphs in this presentation. And it's most impactful for long context workloads, so for the ones we mentioned at the start. For future work, I'm kind of interested in, like, could we do like an adaptive threshold, or could we potentially set different thresholds per layer? I think somebody tried that, but it turned out that getting the correct threshold is really hard, but maybe we just need to look a bit deeper. I'd also be curious to see if we could combine it with some of the existing sparse attention techniques, whether we could benefit in multiple ways at once. There are some links on this slide to, I think we have a paper and various blogs. I appreciate you can't really click them while it's on this projector. Yeah, I think that's my last slide.
Awesome, thank you very much.
You're not going to make me throw the cube, are you?
No. He's got some questions. Oh, excellent. Look how far.
You can't ask your question now, you didn't catch it.
Hey, thanks for the talk. That was super interesting. Can you use this during model training? And if you did...
That's a great question. I think I'm an inference person, so I'm not the best person to ask about that. I think in the paper that I've linked there is a mention to training, so it might be worth having a read. I can also probably speak to some of the training people at work and get back to you. So if you want to talk to me during the networking, we can exchange details and
Cool, will do.
find out.
Thanks again. A lot of that went above my head, but I noticed in one of your parameters you use in an instruct model. So is this what you're trying to do restricted to? I think it shouldn't be, but is it restricted to model types and model categories?
No, I think...
Or can you use it on all flavors of model?
You can. It's basically a drop-in replacement for attention. I see no reason why you couldn't use it for anything else. You'd obviously have to do your own testing on whether you'd be happy with the results or not, but there is nothing. I guess what you're actually asking me is there some constraint in the kernel that means this wouldn't work with a non-instruct model? And to my knowledge, the answer is no. It should be fine.
Cool, thank you.
Any other questions?
To make you work really hard.
Yeah, I'm going to do underarm this time. I could see Tom really worried behind.
You said you used Anthropic Claude codes. Why not Nemotron?
Because, honestly, the day I wrote this presentation was the first day I got a Claude co-work license, and I decided to try it out.
Where's the mic? Sorry.
I feel like every time I go to work, we've got access to another AI tool that's amazing at another thing, and my toolbox of AI tools to use at work is so large, I almost struggle to pick the correct one.
If no one's asking, I can Since you've got a whole suite of models, access to internally and externally, have you tried to benchmark across a whole bunch of these models? And do you have like a result set somewhere that we can look at?
There may be a spreadsheet internally. I would need to check. Certainly, when we were developing this, we had interest from clients. I think there was a few times I got an email from some people. Someone's asking me about skip softmax. Is it ready? I think a lot of the SGLang community were interested in it, which is probably why that PR went out so quickly before VLLM. But I think, yeah, there probably is some data, but if it exists, I haven't seen it.
Okay, cool. Interested in that, if you can release.
Awesome. Any other questions? All good. Please give it up for Dom again.